pleasure to introduce Mike Seltzer. He's joining us today from Microsoft Research. Mike got his PhD with Rich Stern at CMU, and he's known largely for front-end and model noise robustness, and that's what he's going to be talking about today. But the other thing, if you're meeting with him later in the day, that he's particularly deeply involved in is deep neural networks for speech recognition, which is all the rage if you've been to a conference lately.
So, thanks, Aaron, for inviting me, and thank you guys for coming. Let me know if you can hear me or can't hear me. It's nice to see that nothing has changed since I was in grad school, and the first few rows are still totally taboo to sit in. So it's good to know some things haven't changed. I'm going to talk about some work we did recently, or that we're doing recently, that I'm doing recently, in acoustic model adaptation, specifically focusing on some issues that have come up with some of the newer systems that we've been deploying that is somewhat different from sort of some of the standard tasks that we've been working on over the years that sort of have come out through government programs. So before I get in that, I just kind of want to say I feel like it's a little bit of a golden age for speech recognition. So if anyone here is sort of in that area and in the language processing space, I think it's a really great time. I mean, I can't really know a previous time where there's been so many mainstream products that are using speech recognition. So pretty much, probably almost everyone here has a smartphone that has some kind of voice input, whether it's cloud-based voice search or voice dialing, and there's all the sort of major players in the space. A lot of the cars now have speech systems. In fact, it's really amazing to me that that's gone from just a few years ago being $1,000 or $1,500 add-in only to Mercedes to now it's a sort of standard feature on a lot of Fords. And on the lowest end Ford, if you pay a few $100s, you can get a pretty nice voice system. And then lately, this if you don't know, is the Kinect peripheral for the Xbox, which has kind of brought hands-free gaming as sort of the big win with that into the living room. But really, that also has it's the first sort of project that has hands-free speech recognition from a distance. So it's from sitting on your couch, you could be sort of browsing the Netflix catalog. In addition to all these great applications and products that everyone's using, there's also what I would say this sort of fire hose of data now, mostly because these things are connected typically to servers. And so for some applications, you generally, we've gone from this problem of we don't have enough data to now we have so much data, but we don't know what to do with it. So in addition to, in spite of all this goodness, I also want to say there are still lots of problems that remain. And here's sort of my kind of laundry list of the things that I think are sort of considerable challenges in the field. And I think a lot of these, talking with some of the people here today, are things that you guys are dealing with. So like language expansion. So how do you get, you have something that works well in English because there's lots of data, but now you want to go to some low-resource language, how do you build that system? Or even if it's a high-resource language, how do you get the right data? How do you build applications? There's a ton of people who can build iPhone applications and Windows applications and Android applications, but no one, you still need too much expertise to build a speech application. Data resources is something that I think lots of you guys are working on, this low-resource area. And the interesting, a lot of this other stuff comes around with the nature of the application. So once you put these things on a phone, all of a sudden the number of places you can use these things is just infinite. It used to be, okay, I'm going to build the system for the car. It sits in the car. I'm going to build a system for the desktop. I know it's going to sit in the desktop. Now it's the system goes with you. So anywhere you go, the system can go. And so the number of environments are huge. And it's essentially been commoditized, so now everyone has one. And so now the speaker population is also enormous. And then if we go a little bit lower level, it used to be that we'd be recognizing things like phone conversations or meetings where sort of the same person would be talking for 10, 15 minutes up to an hour. Now, if I'm lucky, the person will say, Starbucks, and that's it. And that's all you have. And if you're lucky, they'll call back, maybe later in the day, and they'll say McDonald's, or I don't know, whatever. So basically, you get a word or two, and that's all you have to do with it. And so a lot of the techniques we've been working with over the years that are data intensive kind of have a problem now. And so these last three are sort of the area that I'm going to try to focus on in this talk. So the problem with these areas is that recognition systems, since they're statistically trained, work best when the test data matches the training data. And in mobile applications specifically, like I just said, there's acoustic mismatch caused by the speaker and the environment. It's sort of inevitable. It's going to happen. And so lots of people over many years and lots of ICASP sessions have proposed various ways to change this. You can do enhancement, sort of take the signal processing end of things where you're sort of trying to clean up the signal to take the noise out. Or you can do adaptation, where you say, I'm going to actually update the models in the recognizer to sort of better match the data I see. And that's adaptation going to be the focus of this talk. And so I kind of briefly want to touch on, by way of a quick introduction, the two sort of schools of thought or two different branches of doing adaptations. And so one is something that, and these go by different names depending on who you talk to. And so what I like to say is one is sort of parametric, and the idea is that they actually try to impose a physical model on the system on the adaptation you're trying to do. So to try to take some knowledge from the world into the system you're using. And so the canonical case is for noise robustness, trying to adapt the model to noise. You can say, I know that I have some clean speech that's been passed through some filter, that's H, and then to that gets added some noise from the environment, and then what the system actually receives is Y, is the noisy and potentially channel corrupted version of that. And so what I want to do is now have a recognizer that is good at modeling Y instead of good at modeling X. And I can do that by imposing knowledge of N and H onto the system. And if you do that, you have methods like parallel model combination, which is sort of, and vector Taylor series adaptation. And these are two sort of landmark algorithms from the mid-90s, which are still sort of the standard bearers in this field. And the pros about these is that they're extremely data efficient. I mean, it's actually remarkable that you can just take, if you just tell me what the mean estimate of if you assume your noise is Gaussian and you tell me what the mean is, I can adapt every single parameter in the recognizer. It's all you need. And if in fact the distortion you see matches this physical model, the performance is really great. The bad news is it's computationally expensive because it tells you that actually every Gaussian in the recognizer needs to be updated, which means potentially these things have hundreds of thousands of parameters or more, and you have to do some kind of update on all of those. And the thing is also that not only does the system, that the data you see have to obey the physical model, meaning that you have to have clean speech that's corrupted by noise, but it means the recognizer has to obey this model too, which basically means the recognizer has to be trained from clean speech only. And of course, all these systems we know get better the more data you have. And so if I deploy a system, the data that comes back to me is going to be noisy. And it means I can't use it to retrain the system. And that's kind of a deal breaker. So the other step, the other kind of family of models is data-driven techniques. And these just say, I don't care what the distortion is. I'm just going to use some kind of data-driven approach to reduce the mismatch in the data. And so here you can say I have a bunch of Gaussians. I want to take some observation data or some adaptation data, and I'm going to make the system model that data better just by moving the Gaussians around. And I don't care if those Gaussians got moved because of noise or because of speaker effects or whatever. So what's nice about it is it's agnostic to the source of mismatch. And it also can compensate for kind of any mismatch jointly. So if you have a number of different things that are causing the recognition performance to degrade, you can kind of handle that all at once. And the general purpose. So people proposed this initially, these methods for speaker adaptation, but they've turned out useful for lots of other things like noise compensation or accent. And they also make no assumptions about, because they're strictly data-driven, they don't make any assumptions about the models or the features. The downside is that they require sufficient training data, but lots of people have come up with ways to get around that problem, so it's not quite such a deal breaker. But I kind of want to go back to one of these things. Let's see if I get there we go. If you look at this idea that they're compensating mismatch jointly, that's sort of a plus. But as we're sort of looking at new applications, it actually also turns out to be a little bit of a minus. And I want to sort of take a little bit to talk about why. So let's assume we have a system, and this is the paint by numbers introduction to speech recognition, I would say. So the system, you call up a system. Let's say it's a server-based mobile system, and the system gets observations from some user Joe. And so the system sees these purple observations, we call them Y, and the system says, well, aha, all my models are trained from white-colored data, not purple data, and so clearly I need to do some kind of adaptation. So I'm going to do the adaptation. I'm going to learn a transform that can map the white-colored data to the purple data. And now I say, now I can do a really good job recognizing this data. And I know this data came from Joe because I have the ID from his phone. And so I'm going to log it and to say, this is Joe's data. Next time he calls, we're going to be ready to go. And we'll be all set to give Joe a really good customer experience. Well, the next time Joe calls, we say, aha, it's Joe, let's load up Joe's model. But it turns out now Joe's observations have turned orange, and it's because he's in some different environment. So if you'll notice, before the speaker, the part that was attributed to the speaker is red, and the environment is blue. It made it purple. Now the speaker is the same, but he's in somewhere else, and so now the data is orange. And so now I load up Joe's models, and they're still a mismatch, and we're not doing as well as we could be doing, and you could, in fact, be hurting performance. So what we really want is a way to adapt the recognize or adapt the parameters of the system in a way that separates the variability so that we can say, okay, we saw the data that was purple, but we know that that can actually be broken down into a red and a blue component, and we can actually then store the speaker-specific component and potentially the environment-specific component as well, but store them separately so that when things happen next time, we know, things may occur in a different way. And so to do that, that's sort of what we were talking about during this talk. We're going to talk about this idea we're calling a factored adaptation. And the idea is to explicitly model the sources of variability. Rather than saying this is a one-size-fits-all adaptation scheme, we actually want to explicitly model the different sources of corruption. And in this case, we're talking about speaker and environment, but I also would like to point out for people not interested in speaker or environments that you could potentially do this for any other sources of mismatch in there. So if there's an incentive to hang on and get through this talk, there it is. Please.
So just go back to the previous one. So to be able to break down the last one into the part that's really due to Joe and due to the environment, either you need Joe in lots of environments or you need lots of people in the same environment.
Yes.
Which way are you thinking is more practical, or what happens in real applications?
So we'll talk about both. Or you could, yeah. So basically, the idea is to essentially have. Currently, we've been looking at lots of people in lots of environments and sort of putting them all together. Yeah. And so and there's different ways to slice that up, basically. And that's we'll sort of the details of that is sort of what we'll talk about. And of course, if we can get into sort of where it works and where it needs some work. So we're going to do this using linear transforms. So this is sort of like the MLR and its variants because they're efficient and well-studied and effective. No restrictions on the features, the data, or the training criteria. So it means you can use whatever latest, greatest features you've come up with. You can use whatever training criteria to train your models. And there's no assumptions about the nature of the variability. I should point out that there's some related work on this, and mostly it applies in the space of performing joint compensation of the environment and the speaker. And this is sort of I looked at it last night and thought it sort of reminded me of two bowls of alphabet soup. So one is all the algorithms that have been proposed for speaker compensation or speaker adaptation, and on the right is all the algorithms that have been proposed for environment-specific adaptation or compensation. And you essentially, if you pick one from the blue bowl and one from the red bowl, you'll get one of the papers listed there. And so the interesting thing to me is that sort of this idea of joint compensation was looked at about 10 or 11 years ago, and then with the exception of joint factor analysis and speaker verification, which is sort of a lot of the inspiration for my work, there's been almost no work on this until recently, and then over the last year or so, people have sort of started looking at this problem of jointly compensating speaker and environment all of a sudden. Okay, so if we take factored adaptation, the first case we're looking at is just the CMLR case. So if we take a CMLR transform that's constrained MLR, it's a model adaptation scheme that can be implemented as a feature transform. And the nice thing here is you can basically represent this instead of with a single transform as a cascade of linear transforms. So you basically have two transforms. One's going to model the environment and one's going to model the speaker in this case. And then if we have linear transforms, we know, because we know how to do MLR and CMLR, then we know how to estimate these using maximum likelihood techniques. Now the challenge, of course, is a given CMLR transform, so if I take the first equation, can be arbitrarily factored into any other set of transforms. And you want to avoid that because you actually want these transforms to be meaningful so that you can then reuse them in some way that's effective. And the way that we're going to do that, and this sort of gets to the point you were alluding to earlier, is that we're going to assume that we have some sets of environments and speakers that are just basically not fully overlapping. I'm sort of trying to figure out what the minimal set of restrictions is, and I think that's basically it. And then we're going to assume that we have either known or estimated speaker and environment labels. And is this a reasonable assumption? Well, I think it depends on the application and, your funders and stuff like that. But basically, for a lot of the applications that we're concerned with, having a speaker ID is reasonable because generally there's at least a device ID associated with, or a user login associated. The environment label is a little bit dicier, and so we can talk about that. And so the idea basically becomes just to estimate the transforms using EM on distinct but overlapping sets of the data. So the idea is you're basically going to group the data by speaker and environment, and you can iterate this process. And this is very much inspired, I don't know if anyone here is familiar with speaker verification, this joint factor analysis where they're doing map adaptation, where you have, and in map adaptation you get an additive offset, and they have an additive offset that's associated with the, they call it the channel, which is basically the environment, and there's an additive offset associated with the speaker. And if you train it that way, you can get just the speaker-dependent part, and that's good for speaker verification. And so this is very much inspired by that vein of thought. So because I like pictures more than equations, this is sort of the algorithm. And the idea is you can imagine that you have, let's say we have 3 speakers and 5 environments, and assume we have labels for now. So you can think of the shape represents the speakers. So the triangles are speaker 1, the circle is speaker 2, the squares are speaker 3, and the color represents the environment that those speakers that data happens to be in. And so the purple is environment 1, the green is environment 2, and so on. And so the idea would be that you'd partition the data by speaker, estimate some kind of speaker transform. Then you'd repartition the data by environment, keep those speaker transforms fixed over all that data, and update the environment transforms. Then you'd repartition the data again for the second iteration back by speaker, keeping all the environment transforms fixed. And you're sort of doing this process iteratively back and forth until and this is, this ping pong sort of EM maximum likelihood algorithm. So this is sort of the basic idea. It's pretty straightforward. It's pretty simple, I think, to understand, hopefully. So the preliminary experiments we tried is on, we sort of said what's the simplest way we can evaluate if this idea has any merit at all. And so we tried this on Aurora 2, which is, if you're familiar with or if you're not familiar with the task, it's sort of the canonical noise robustness task. It's noisy connected digits. There's a variety of environments, and there's a variety of speakers. And the baseline system is sort of the most reasonable, sort of good backend you can do as a baseline. It's the complex backend on the multi-condition training data. And again, our goal is actually not to do the best speaker adaptation in a multi-pass scenario. The idea is how much can we make the transforms that we learn at adaptation portable? How much can we carry them from one environment to the next? And so we looked at test set A initially, and that has 4 different environments at 7 SNRs. These are the environments: subway, Babel, car, and exhibition hall. These are the same environments and noises that are seen in the training data. So that's why this is sort of a matched case. There's 100 speakers and plenty of utterances, 70 utterances for each speaker. In this case, we're going to consider the environment to just be the noise type, not the independent of SNR. So all the SNR levels of subway is one environment, and Babel. And so we have 4 environments, basically. And so just to get an upper bound to say, hey, can CMLR do anything in this case at all, we're going to estimate one transform as a sort of per speaker and environment combination. And we're going to do unsupervised batch mode adaptation on the whole 70 utterances, and then do a second, a re-recognition. So that's sort of the upper bound for CMLR in this context. And if you do that, you can see this is the baseline. This is the word error rate by SNR and the word error rate by environment. And you can see, we get reasonable gains across the board. So it does say that yes, a linear transform applied to the features does have the capacity to improve accuracy in this task.
Mike, the error rates, of course, look very small, so maybe you should tell those of us who don't know what the task is.
Oh, sorry, I thought I said that. Sorry.
But I don't know
Oh, it's connected digits.
Okay.
So it's a 10-word vocabulary, no language model, strings between 0 or 1 and 10 digits, I think.
Word is basically the whole number sequence.
What's that?
When you say word error rate,
Oh, it's a digit.
oh, 1 digit.
Yeah, is a word.
If I said 3, 5, 7, 9, then that's 4 words.
Yes.
Okay.
And on this task, state of the art, best ever is about 94.5%. So about 5.5% word error rate, and that's what the sort of on average over all the sets. And if you did CMLR with a speaker with adaptive training, I think you get pretty close to that. So it's in the ballpark. Okay, so now we said let's look at how well these transforms that we've learned in sort of the best case for CMLR work across environments. And so we're basically just taking the transform we learned for a given speaker in the subway noise, or noise condition 1, which is the subway noise, and we're take that transform and just apply it to the other noises. Same speaker, other noises. And it turns out that you actually lose almost all the gain you had in the first case. So the red is basically the previous result summarized over all the SNRs. And the green is what happens if you take the transform from a particular environment and apply it to the same speaker in different environments. This sort of indicates that there's something being lost by the fact that you're doing this joint compensation over different environments. So now we said, okay, let's try to do some experiment where we're going to do this factored CMLR approach. And the idea is to say we're going to take the training data and we're going to learn a bunch of environment transforms on the training data. And implicit in that, we have to learn speaker transforms on the training data, but the speakers aren't seen, so those are sort of essentially thrown out. Maybe we could do that with supervised MLR because it's seen in training. It's training data. And then we're going to estimate the speaker transform on the same data, that subway data again, but this time we're going to apply the subway environment transform first. And so now the idea is that you have you have a transform on the environment that's absorbing the environmental variability. Everything you learn is going to be specific to that speaker, and will help you generalize that transform across to other environments. And then we're going to apply that speaker transform to the other environments in the same way we did before. And so if you do that here, now you can see that's the purple curve that we've gotten back basically most of the gains we lost when we sort of tried to take the same transform across environments. And so this seems like a good indication that this sort of method has some merit, and that generally trying to have transforms that are supposed to represent the speaker, but they're also capturing environment, can be problematic when you take those across different environments. So this sort of is our pilot experiment. But of course, in this case, if I want to use the meme of the day, I could say, we had to use environment labels, and you say, really? Is that seems sort of weak. And so the idea is now to say, okay, well, let's try something, a little bit, how would I say, a little bit more realistic. And let's say we're not going to use the labels from the environment anymore. We can still assume speaker labels. And so the idea is now we're just going to do some clustering of the environments we see in training in some unsupervised way. And here we're doing something quite simple. We're just going to say, okay, let's look at the silence regions, the pauses of all the utterances, do some kind of clustering, so you can, whatever your favorite clustering technique is, and then essentially learn a transform for each cluster. And then at runtime, you're going to estimate the environment for the test utterance based on the closest cluster. And the nice thing about doing it on the silences is that you still can do it in the first pass, because essentially you're going to get the initial. There's always a few a second of silence or so before you start the speech, and if you can use that to determine what environment you're in, that means, and the speaker from the caller ID, it means you can actually apply these transforms in the first pass without having to do a second pass recognition. Yeah.
With something like babble noise, how easy is it to know where silence is?
As long as the SNR is not 0 dB, it's pretty reasonable.
15 or 10 dB.
It's okay, yeah, yeah, and I mean our especially because in this, I mean we found that it's okay to do, because generally the other thing is also it's a lot of these, there's in a lot of these utterances, they're generally push to talk to start. And so then you're sort of listening, and then all of a sudden, it's easy to detect the start of speech from that, because it's clearly a difference. If this was a sort of a always-on scenario in a bar, it may be much harder for sure. So this I think is 10 frames. So it's very short. And I also want to make it clear that there's lots of people who've done lots of great work on. They call it acoustic sniffing, which I think is kind of a weird term, but it's sorry. But basically on sort of environment detection and classification, and this is by no means anything remotely close to state of the art in this field. I just sort of said, okay, let's just try something simple. So now we've tried this again on repeat the same experiment, but now assuming that the environment is unknown. And so we basically it's basically the exact same experiment, except now we have test set A, which is the same experiment we repeated before, where the environments are the same as they are in training. So even though we didn't have the labels, it's the same types of noises. And then set B is actually a whole bunch of different noises. In that case, all we're doing is saying what's the closest cluster to what we have. It's nothing clever. There's lots of other clever stuff we can do, but we're saying let's just find the closest one and use that. And so, not surprisingly, I think I sort of expected on the scene environments, it works. You still get a nice gain in this case. However, I was actually kind of a little bit surprised that it worked pretty well even on the unseen environment, which to me says that even if you can't sort of absorb or compensate for the environmental variability perfectly, doing something is better at will let you capture the speaker effects more accurately than nothing, essentially. And obviously, the more data you see, the more you could refine this process. So, okay, so this is a sort of a good place to sort of take a quick break and sort of see where we're at. And so hopefully what I've tried to show, at least so far in this small task, is that this general approach seems reasonable, and whether or not you implement it in this particular exact way, there's lots of other ways, but potentially this idea of separately compensating for the speaker and the environment seems like a reasonable thing to do, and a useful thing to do if you're interested in carrying data over across sessions from recognition. But there are some potential issues, and sort of I glossed over a lot of the mathematical details of this, but if you go through it, and I'm happy to sort of go into it in more detail. If you do this cascade of CMLR transforms, it actually requires transformation updates that are comparable to running adaptation with a full covariance recognizer. And as a result of that, it becomes more complicated computationally to do if you have this sort of large scale systems and millions of users and you're trying to do this sort of all at the same time. So that's sort of thing number one that is a potentially snafu. Thing number two is that we looked at, we were saying we looked at just the pauses for the environment clustering. And I don't want to call my own work cheating, but basically, you have Aurora, you have this task, and the task is additive noise. And so if you say, I'm going to look at the pauses, can I detect additive noise? Well, of course you can, right? It's sort of a, yes, it's sort of a, that was sort of a environment clustering game to the task. And the question is, in real data, is that still going to work when the data is out in the wild? Is it when your data is not subway noise versus train noise versus restaurant noise? Is it as easy to do environment clustering? And then the final thing is, how do things look on real data? So if we looked at systems that are sort of more state of the art, how does it look? And so basically in the remainder of this talk, I'm just going to try to look at version 2.0 of this algorithm that's going to try to sort of address each of these aspects. And so, please.
You had this nice comparison of seen noise, even though you don't know which one it is, versus some unseen noise, again, not knowing what it is. Instead of dealing with the first few frames, has anyone, or maybe you looked at saying, let's run all our models concurrently and take the one that has the highest likelihood?
Yes, in slide 27, we'll talk about that.
Because what I was thinking, the other question was, did you try sneaking in segments with no noise to see what happens? Like one of your unseen noises could be no noise.
Yeah. So in all of these, I can pull out the number, but actually, I have the number. Yeah. So the last row is clean speech. So this is with no noise, and so.
But you still have a noise model in there.
Yeah.
This one I thought was with knowing the noise condition.
Right, but the noise. So the bit here is
zero babble noise, meaning there is no noise.
Correct. Yeah. So the system was so each in the training data the noise subway had SNRs from I think 5 dB through clean, and so even though some of those examples had all those were lumped together as one environment. So there was a little bit of, basically what it ends up is there's some clean speech in all the environments. And so you're still forced to choose a transform, an environment, right? And so and in theory because there's an equal, I think in this setup there's an equal amount of clean speech in every bin. It should be a random choice which transform you pick. But I don't remember. We can look somewhere. I have a full matrix, because you can get these results at a very detailed level of noise, SNR, and stuff, and we can see it. But in general, I mean, the clean performance, I think, was may not have been a big gain, but it wasn't hurt because that's actually one of the most one of the most important things I had to wrap my brain around from going from academia to industry was you cannot hurt the clean performance, right? You basically, because if you take a really the low something where there's 40% accuracy and you improve it to 50% accuracy, you've just gone from useless to useless. And if doing that has taken you from 99% to 98% accuracy for the clean speech, then you've gone from useful to you've introduced twice as many errors in a useful scenario by helping nobody at a useless sort of error rate. So, okay. Any other? That was it? Okay. Okay. So now we basically just do this is the idea here is basically, can we just, instead of doing a cascade of feature transforms, just to simply do a combination of feature transform and model transform. And it's not maybe it's not super profound, but it actually turns out to be actually reasonably effective. So this is now the idea is when you're evaluating this distribution, you have a transform on the features that essentially is taking care of the speaker, and then you have a transform on the model parameters itself that's taking care of the environment. And the interesting thing about this, what's not interesting, what's nice about it is now you can actually use the standard recipes for estimating these things. You don't need the full covariance estimation, which is it's doable, and I've implemented it, but it's much nicer to be able to use standard sort of recipes. So here it basically becomes the algorithm becomes the same exact thing, except now when you're implementing, when you're running the MLR part, you basically have appropriately adapted features with the current estimate of the speaker transforms, and then when you're doing the updating the speaker transforms, you basically run the standard CMLR at estimation with the appropriately adapted model parameters. And the otherwise iterations proceed exactly as before. So that's sort of the first thing that we sort of wanted to improve on the algorithm. The second thing was sort of this idea of the environment clustering and sort of the idea of potentially maybe having this additive noise detector is not quite what we want. And in fact, I think once you start looking at the real data, this notion of environment can be a lot more subtle than just noise type, right? It could be, if we're going to lump the data, I would say, to me, what we're really trying to capture here by environment is any variability that's common across speakers, right? And that can be anything. It could be noise, it could be reverberation, it could be iPhones versus Android phones, it could be the codec you use, it could be maybe even it could be just accents could be in there. I mean, it could be anything that's common across multiple speakers. So if this is the notion of environment, if you really want to generalize the algorithm this way, then labels based on pauses are suboptimal because the differences again are only going to show up in additive noise. And I think which gets to Sanjeev's point is that you now have this disconnect between the objective function you've used to try to find the clusters and the objective function that you're using for adaptation. And so we actually wanted to address that with essentially a maximum likelihood clustering, which is, I think, what you were saying. And the idea is basically just use the recognizer itself to decide the clusters. And so you could say, okay, at any given iteration, I have some number of transforms. I have speech from known speaker. I'm going to try all the transforms, and I'm going to pick the one with the best score as the cluster belonging to that transform. And then what's nice about this is it's actually symmetric. And so you can actually do this for figuring out what the environment clusters is. And now it lets you go into the other case where maybe I don't have the speaker labels either. And so now you can actually flip it around and say, I can actually now, fix the environment transforms and try a whole batch of speaker transforms, and again, cluster the speakers in this way. And this while it can be done, at least in the tasks that we're looking at, this would be it would be computationally it'd be burdensome because we have speakers, tens or hundreds of thousands of speakers, but you could do it, either this or a proxy for this I think would get you pretty far. So this then turns the previous algorithm into this sort of 4-stage algorithm where you have an integrated clustering and adaptation approach, where one AM iteration just is a full cycle around this chain, where essentially you're going to update the speaker transforms. With the new transforms, you can update the speaker clusters. Given those clusters, you can then update, and the transforms, you can update the environment transforms. Given the transforms, you can update the clusters, and that sort of consists of one iteration around this loop, and you can go around this loop until likely it converges, or until you get kicked off the cluster farm. So now basically this is we're going to try this, and so the third thing, remember, is does this work on real data? And so this is our system now we're going to evaluate this on. This is Bing Mobile Voice Search, and this is an application that is on the Windows phone, is also on Android phone and on iPhone. I encourage you all to install it. It's a great application, and try it. The training set we have is 300 hours of speech. It's been I'd say roughly transcribed, as I guess is equivalent to sort of rapid transcriptions in the switchboard domain. We have 5.5 hours of speech for the test set. So it's 20 utterances from 270 speakers. Now, this test set was chosen specifically for running these kinds of adaptation experiments. And so the test set consists of, if I get it, all the speakers in the test set have at least 20 utterances in the training set. And so there's no unseen speakers. All the speakers we have training data for, which is what we're going to use as the adaptation data for that speaker. But I also want to point out it's not like this is matched, because these 270 is a very tiny fraction of the total speakers. And there's probably 10 or 20,000 speakers at least in the training data. The other thing that's interesting about this is much sort of more representative of a state-of-the-art pipeline, in that we just sort of do normal MFCHT processing, and then we do HLDA. But prior to that is actually doing some speech enhancement, signal processing kind of cleanup of the features. And so what's interesting is that in the previous case we were saying in the Aurora experiments, let's really, our environment is additive noise. But if you're really trying to build the best system you can, what we say, we already have lots of techniques that can address additive noise, and it would be stupid to throw those away. So actually, this is being run on denoised features already. And so if there's any kind of stationary additive noise, we're already doing a good job removing that. So that by definition, in this task, environments is sort of moved beyond that scope. Maximum likelihood training, and then for adaptation data, we don't have any knowledge of environment. But we're going to use the device ID. So every query has a metadata associated with it. And one of them is sort of the ID of the phone. And so that becomes our speaker label. And of course, there's the odd case where someone hands a phone to a friend or to a spouse or something. But by and large, I think I'm not really worried about that. Yeah. Reverberation. So like the fact that when you talk, is that enough? Okay. So, and then another one would be codec noise. So the way the speech is actually encoded on your phone. So like most phones use GSM encoding, and so that's a nonlinear distortion on the signal.
Is the additive noise, is that problem solved, or is it still?
No, I would say additive stationary noise is mostly solved. Additive non-stationary noise is still a big problem, and it could be like, so like if you're in your car and and you accelerate, even that is non-stationary, and of course like music is sort of the worst case of not worst case, but a sort of more typical example of non-stationary noise.
What's the OOB rate in the test? Or is it OOB?
Is it what? Oh. So no, this is a word error rate we're looking at. It's, I want to say it's around 5% or 8%. Yeah, and this is actually being run with. I thought I put it in. So and this is actually being run with 60. It's even smaller. This is like a 65K vocabulary, which is about half of what our production system, uses. So.
You said that there's overlap in the test.
Probably not in user end query, but probably query is probably overlay. Yeah.
That's what I mean.
Yeah. I don't. I to be honest, I haven't actually checked, but yeah, if the same guy asks for Starbucks every single time, then there will be overlap. I didn't actually filter the data that way, but yeah. But this is so this is only the 65K vocabulary trigram sort of standard language model. Right. And I also should point out that there's a lot of other things. You get into a whole bunch of other things with this task, which, there's a ton of text normalization and inverse text normalization that should be done or can be done, and there's only so much you can do. I mean, at some point, so for example, I can't think of, obviously like, QFC is a grocery chain in Seattle, and so whether it's Q period, QFC or QFC, I mean, you can write you can come up with a bunch of fancy ways or simple ways to sort of count errors, and how do you count those errors? But there's always ones I'm sure that you'll miss. So just scoring these things is a challenge for sure.
My back of the envelope calculation says that each utterance is about 3.5 to 4 seconds long. Is it just short phrases?
It's
silence?
So it's some silence. It's generally a couple of words. I think 3 to 4 words is or 3.2 words is sort of the average query length. So so it's very short. That's the thing actually. So we actually have, if you do sort of the standard 2-pass, sort of the thing everyone sort of does is you could sort of say 1 pass, CMLR transform, do a second pass. And there's not enough data to do that kind of thing, which is really why we're looking at this sort of, can we batch up the data over time to do some kind of personalization.
So this means when you say 300 hours of speech, it's really like 300 hours of audio and 100 hours of speech or something?
It's like maybe it's over 200 hours. The audio is about 200 hours, I think, or 100. What's that?
The speech is, in other words, like...
Yeah, this is 300 hours of audio.
Okay.
Yeah, that's right. So, the amount of speech is 180-ish, I think, or something in that ballpark. Okay, so here are the results. This is a sort of baseline result for CMLR, and I think as those of you who have run these tests or these kinds of experiments know, you always have these small tasks and you get these giant gains, and then you run the big tasks and the gains, shrink. So, but such is life. So a couple of interesting things with sort of normal. So again, this is taking 20 utterances from that speaker from the training data, learning a transform and applying it to that speaker's test data in the first pass. So so the baseline is about 31 it's 31.6. If you do a single CMLR transform, it gets you a small improvement. So now the interesting thing is now you can say well, we know there's non-speech in there. Let's do a 2-class transform where we have 1 class for the speech and 1 class for the non-speech. So I found this really interesting is that if you do that, you actually get worse performance, and that I thought was really promising for me for this kind of thing, which basically is because obviously the non-speech transform is learning whatever is the noise, what's in and it says that whatever you're learning in the training data in the noise is not generalizing well to the test data, and so I found that. Which means if it's not generalizing well for the test data in the pauses, it's also not generalizing. It's also having some detrimental effect on the speech as well. And so if we can handle that, that'll be promising and effective. So then the interesting thing is, okay, well, if that's what's happening, let's do the same exact experiment, but let's just turn off the transform for the non-speech. And so we're saying, well, we're going to assume we don't know anything about the pause part. And so the idea is you take the non-speech class and you reset that transform just to the identity matrix. And if you do that, you actually get almost double the gain you do from just a global transforms, which it says that and I think this is all good evidence that what is in the background besides the speech you care about is really potentially polluting the speaker transform as you look over the data, as you look across sessions.
And last time is only because you have these 20 plus utterances from the speaker's training. This wouldn't be possible for speakers from which you have Why copying because the non-speech transform is obviously picking up something about all the non-speech that appeared
in the training, right? And so I think what my assessment is there's a lot of variability in the non-speech over those 20 utterances, and you're modeling that with a single transform, and so you're getting some kind of average, which may not be helpful. So what the experiment I didn't run is if you use that transform to re-recognize the training data itself, I would expect it will help because it's on the same data.
Why is that a more natural way to compare for performance?
Because this is the metric that our colleagues in the product. No, so I mean we have a bunch of internal numbers on this for a bunch of different systems at the word error rate level, and sort of. I mean there's a correlation. I can actually go one. I can take you one better, which says, and there's actually been I think there's an interspeech submission on this from a colleague, which says what you really care about is do these words find me the right web page or the right search result. And so even if the query is wrong, but lots of people say that the wrong way, and the search engine can flip it, can still get it right. We don't need to correct that error, right? And so.
There's a lot of ways. So say the word error rates were solely in function words, like it always said the with them.
Yeah, but how many function words are voice queries? I don't say the strings.
No, but I mean there are some things with the.
No, you'd say the star. No, I'm just kidding. Sorry.
I think that's a.
I think one can imagine that.
Well, so the other thing I should say is that we have we do the same. We have this system that also processes other data like. So no, I mean I guess I agree with you that query sentence error rate is equally valid, or is maybe more valid in this case. They're obviously the higher. I think for something like this, I think it's in the. But it's because there are so few words per query. It's not. They're pretty correlated. If this was a long sentence, I think it may be different. But I think it's like in the 40s, mid 40s. So that other paper we were looking at this morning was that one as query error rate. But the other thing is there's also, I think, generally what happens is we have these systems and we have this is one of several test sets that we have, and others are like SMS dictation. So in that case, word error rate is sort of more natural. So it may sometimes it's just easier to have a consistent metric. But a lot of these things are just sort of, I think they're all correlated to some degree, and it's in some sense it's in the eye of the beholder. I don't really have a great answer. Okay, so now we're going to try the factored adaptation. We're going to essentially divide use I would say three cycles of the four-step process I described earlier for adaptation. So we're basically not going to update the speaker clusters because we're going to assume that the labels we have for the speakers are accurate. So essentially using three branches or three boxes in the grid. The initial, again, because this is all a local minima finding kind of thing, the initialization point is important. So we actually still do looking at the silent segments to do an initial estimate of the clusters, and then they're refined on each iteration. I shouldn't say speaker transforms fixed. I should say speaker clusters fixed. Sorry. So we update all the transforms, speaker and environment, and we update the environment clusters. The speaker assignment of utterances to speaker label is fixed, and the decoding basically becomes we know the speaker because of the label, and we basically do n decodes per environment and pick the one that has the highest weight. So this one, it turns out that actually we actually get some improvements just with a simple classification of just two environments. And so here's a comparison of the first column is basically the results from the previous chart, and then the second column is this factored adaptation, and then the improvement across. So we basically get 4 to 5% relative improvement with the factored adaptation. The interesting thing is I think is in this two-class version where you have speech and non-speech, we turn off we saw that it was beneficial to turn off the pause, the non-speech transform for the speaker adaptation. But in fact, we actually, so when we do the factored adaptation, we can actually do that only for the speaker transform and keep the non-speech transform for the environment transform, because that's the part that we're carrying over from, that because it's an environment transform, we actually explicitly definitely want to model what's happening in the pauses. And then I think the last result we have is basically is if these things are actually as portable as we'd like, can they be used independently? So do we always need to run it in this sort of factored adaptation setting where we have an environment transform and a speaker transform, or can we actually run them independently? And so to do that test, we basically say this is the result for no adaptation, this is the result for the best CMLR result we got. So if you actually run this factored adaptation, but you only use the speaker transform, turns out you actually do a little bit better. And if you take only the environment transform, you get you don't do quite as well, but you get some appreciable gain. And of course, if you combine them, you do the best. And I think the interesting thing to take home here is that if you look at what happens if you just do a speaker transform, you're actually getting speaker transforms that potentially generalize better. So even if you're not interested in worrying about the environment part, you just want to do speaker adaptation in this way, you can just use this as a way to get at a better speaker transform that generalizes better to when your data is in unseen environments, whether or not you actually want to handle the environment compensation or not. And the other thing is actually the environment compensation actually does give you a little bit of gain. So even if you have new unseen speakers, you can still do something, because potentially with something that if you have a system that has lots and lots of incoming speech, probably you've seen that environment before, even if you haven't seen the user before. So that's about it for what I have. I would say, the highest level bullet is compensating for speaker and environment mismatch is important for speech recognition. Factor adaptation, what I've tried to present here, is sort of one way of doing so in a way that separates the sources of the variability, which is very desirable for using. I like to say it's sort of getting more utility out of your adaptation data, because it's basically letting you take this data from many different sources with something in common and using that data to unseen conditions. And it's given some gains over standard adaptation techniques. And this is, again, still early, more to come. And so I think I have, yeah. So I just want to point out a few possible things that we're looking at now. Which is right now we've looked at, just because it was sort of the most straightforward experiment to run, the modeling power of the two different transforms were the same. And we know, if you go back to the parametric models, which I sort of talked about at the very first step, where you can actually adapt every Gaussian, you know that theoretically, if you're adapting for things like additive noise or channel, or you should be updating each Gaussian individually. And so potentially, normally we can't do that because we don't have enough data. Well, if you take just this case, we had two environments, and we had 5,000 utterances for adaptation data, which means that we basically have, if you assume that they're half-half, 2,500 utterances, which is a ton of data to estimate the environment transform. So you can potentially have a much more detailed model of the environment. There's no reason why the speaker adaptation and then the environment adaptation have to be at the same granularity. So you can have a very, very highly detailed environment transform, which could essentially be realized as two entirely different, or n back ends and different acoustic models, and you have. Whereas, in the speaker transform could be something that's more higher level, or coarser, like a singular transform or a handful of transforms. The other thing is I think right now we've looked at different utterances just within the same application, but I think it's much more interesting potentially if you could take this across applications. So, for example, can you take, someone's, if someone makes a bunch of voice search queries on the phone, and then they go home and they want to, play a game on Xbox, can we use the voice search data they have to actually give them a better experience in the living room? And so that's, there's a whole bunch of other challenges because the front ends are dramatically different, right? I mean, there's hardly any noise, but there's lots of reverberation. You have the far field effects. It's, the environmental differences are much starker, and so that would be interesting. And the other thing I think, which is also interesting, is right now the idea is we want to take speaker transforms from place to place, but I think for expanding applications to new languages, we could potentially look at, let's reuse the environment transforms instead. So you can imagine that you have a automotive system that's built for English, and if you can run something like Variability Adaptation and get a whole bunch of environment transforms that characterize the car environment, you can then take some, let's say, Swedish data, and then actually impose those transforms on that data, and you can get an automotive model for a new language without having to actually collect a whole bunch of Swedish automotive data or whatever language it happens to be. So I think looking at both sides of how this could be done can help sort of the low resource situations as well. So I guess I reused that bullet twice of more to come or whatever. So that's all I have. So thank you for your attention, and if there's any more questions.
Modeling the environment is interesting because environments are sort of composite, right? So maybe there's a lot of sharing you can do among environments. Not like in this room, there's a certain amount of reverberation, but there are also there are other types of noise that we're going to see some of them in other situations, but not all of them.
Right.
And like there's been some work here in modeling language about how so in Matt's work on selectional preferences, where you're saying I like to eat things that are both food-like, things that people eat, and they're ingestible, but they're solids. And I drink things that are liquid, but they're ingestible. And so I can sort of model these separately, and then I get a lot more signal from both of them. And it seems like maybe there's similar things with the environment.
Yeah, definitely. So I mean, sort of the straightforward is you can imagine that there's an environmental or speaker space. Multi-dimensional space, and so potentially if we come up with one thing that we thought about as a next step is to say, rather than sort of picking an environment as a wholesale thing, you can imagine that this is sort of, if you have all environments represented as with some basis set, for example, right. Then you can have directions in that space and say, right, so like reverberation is some weight on this vector with sort of reverberation, and noise is some weight on that vector. Yeah. So, and I think that's going to be crucial for generalizing this across applications, and like you say, I think right now this is sort of we're sort of going step by step and sort of trying to increase the complexity as we go. But I think in general, I think you're right that if you want this, I think there's a much richer way to represent possible combinations of speakers, and same thing's true for speakers, right? So you can handle speakers you haven't seen before.
So certain people that just left the room have a sort of very strict point of view that noise robustness research should always be done in the clean training condition. Right?
It has changed in the last couple of weeks.
Okay, it might have changed in the last couple of weeks. Reality is maybe seeping in, right? But I think I kind of sympathize with that view that obviously in an ideal world you would be able to handle noise robustness irrespective of whatever environment you're going to be dealing with. That is something you can just factor out from the get-go. I understand, you being in Microsoft, you live in the real world, and you can't fall back to such lofty positions. But do you have any hope left whatsoever that that's going to ever be possible? Or or you just believe you need to have a very solid environment model, and without that, you're going to lose?
I think as long as as long as the system's so strongly statistical, I feel like it's hard for me because I'm a double E guy, but I feel like you really sort of need to take off the engineering hat and put on the pattern matching hat. And so there's a hope. The problem I only thing I see with that is that those are sort of not one-off solutions, but like, okay, so I have additive noise, that's stationary. I know how to handle that. Okay, check. Right. So now I have codec distortion that's nonlinear, so I need a new something that's going to do that. I don't know how to put this. And then you end up with this sort of pipe, So if I give you noise that's, to say that I have closed talk, ISNR, clean speech as the target is just as many things where the distortions are the combinations of things, and so then you would need a block for each one of these things. Yes.
So in my age, maybe I can ask a philosophical question.
which is like, so you, if I follow all your thought, you mainly sort of take the approach that you will model the noise, or you will adapt to the noise. Essentially, noise is there, right? If you look at the communication or information theory, and you listen to Shannon or somebody, they would say, best thing what you can do is to ignore the noise. Basically, something is noisy, leave it out. I mean, it's because noise is ultimate destroyer of information, quoting Shannon. What do you think about it? I think there are two different, fundamentally different approaches. And I kind of almost feel that maybe what I am doing, I'm ignoring the noise to the point that if something is too noisy, I don't even do anything, I just walk out, right? But if there is a part of the signal is corrupted, I feel that what my system is doing is to try not to focus on the corrupted part, but rather go for the part which is not yet corrupted, because very often that's the situation, that a part of the signal, and that's the reason why speech is so redundant and so on, is that we always hope that part of the signal is going to be uncorrupted, if there is any communication happening. So what do you think, I mean, sort of like on this level, kind of?
Yeah.
What is your feeling? I know that your approach is to model the noise.
Right. Well, so I mean,
the noise.
right. Well, I would say that, I mean, because the part that I would, I think that the part that I like about doing when I say model the noise, it's not necessarily, I mean, the part that I actually find most useful when in the model, I have two answers. The first one is, the part that I found most useful or most interesting with modeling the noise is not that I'm necessarily modeling that this is giving you the what the noisy speech looks like in the recognizer, but it's that you're able to actually in the recognizer impose the uncertainty caused by the noise. So that the fact is it's not, so if I just wanted to model the noise, I could change the means of the gases. But the fact that the variances are also changing, to me, says so I actually think that's the model. That's the model version of what you're talking about. Because the idea is that if a given frame is so noisy, and again, if you have a global transform, it's hard to do this. But ideally, you'd like to say what I want the given frame to do is rather than ignore it in the pre-processing step and say don't recognize it, I want to sort of send it to the recognizer with sort of infinite variance, right? So that the decision doesn't actually go through that. So that frame is not used in the decision process. The other thing is, I would say, is I spent my master's and sort of early part of the PhD with this missing feature stuff, and actually recently with this deep neural net stuff, I got back to a little bit of that as well last summer. And, it's just the hardest chicken and egg problem to deal with, which I know some of your students are dealing with, which is yes, if I know that certain parts are noisy, I should punt, but figuring out which parts I should punt on is just really hard.
Well, and that sort of requires a model of the environment to know it's not speech.
Right. I mean, you end up sort of...
No, I think the other way around. It requires to know what is speech and everything else is not speech, right? I mean, that's I think, a royal way of going about that. That's sort of like if it is not speech.
Right, exactly. And I actually think that is the way to go. I mean, the other point is actually versus the sort of alludes to the cleaning versus noisy training data system. It's like, I don't believe inherently. If I take a page from if you look at the physiology, right, I don't believe that our brains are trained for clean speech, right? And that all this periphery is just a denoise.
Yeah, in fact, I would make the argument that if you want to really know what speech is, you can't listen to only clean speech and know what speech is. You have to listen to speech in all environments and say what is essentially common across them. That's real speech.
Right. And actually, and when I looked at trying to figure out which was the most noise corrupted parts of a spectrogram, for example, the idea was to go classifiers that study aspects of speech rather than any aspects of the noise and say, I expect the energy of the harmonics to be blah versus not of the harmonics, the ratio of the harmonic energy versus the aharmonic energy to be something. And then if there's noise in there, it's going to be something different. So that would tell me that there's noise there. So you could potentially try to figure out a whole bunch of these speech-like features.
Yeah, so there's work being done here. I don't know if Shooter's in the room, but they're using these 2D spectrotemporal sort of playing and filtering based on that, and the region that seems to be most consistent with speech,
Right.
and it's having a pretty substantial.
Yeah, so I think that work is, I mean, sort of this is, yeah, I think that work is actually really, really neat. That work is good. Right, I mean, we know that the spectral temporal modulation is for sure.
But that's inherently just going after sort of the speech, right? It's not.
Right, which I think the idea is right. I mean, you can't, I think that the point is you can't possibly know all the noise in the world, but you can try to know as much about speech as you can.
Any other questions? Okay, let's thank our speakers.